Hello, this is YoonhaJang. My research review paper has the title of Ultra-Fast Structure-Aware Deep Lane Detection. This is the list of the contents. First, let's look at the lane detection algorithm. Lane detection is the task of detecting lanes on a road and provide the accurate location and shape of each lane. For lane detection, which is fundamental component in autonomous driving, uses these two kinds of mainstream methods. Because of great representation and learning ability in challenging scenarios, deep segmentation methods of lane detection have made great success in lane detection field. UFast is sought out of deep segmentation-based lane detection. There are two problems of existing lane detection algorithm. Let's see the first problem, which is high computational cost. Present autonomous driving system is commonly equipped with multiple sensors, which typically demand lower computational cost for every sensor input. As modern lane detection methods are mainly based on pixel-wise segmentation, it computes even a lot of unnecessary pixels. So, previous research SAD is proposed to solve this high computational cost problem by self-distilling, which learns lightweight model itself. However, due to the dense prediction property of SAD, the method is still computationally expensive for real time. Therefore, a faster pipeline is essential to lane detection that requires low computational cost. Second problem is no visual clue in challenging scenarios. When there are challenging scenarios with severe occlusion and extreme lighting conditions, it results in no visual clue. This makes results as a segmented binary features and wrong lane location. Previous research at CNN addresses this no visual clue problem by proposing a message passing mechanism between adjacent pixels, which significantly improves the performance of deep segmentation methods. However, due to the dense pixel-wise communication, this kind of message passing requires an even more computational cost, which is fatal for autonomous driving system. Therefore, UFast is aiming at extremely fast speed and solving no visual clue problem. To implement fast speed and solve the no visual clue problem, first main method of UFast is row anchor-based selecting method based on global image features for low computational cost. Instead of segmenting every pixel of lanes based on local receptive field, UFast selects lane grid location at predefined row anchors, only considering lane area of the image using global feature which has larger receptive field. These pictures shows the difference of original segmentation and row anchor-based segmentation. Pixel-wise segmentation computes every pixel in image, so large W is the number of pixels in row and H is that of in column. On the other hand, row anchor-based segmentation computes every grid in row anchor. So small w is the number of gridding cell in one row anchor, and H is the number of row anchor. This illustration shows several pixels located in one gridding cell, which means one gridding cell contains many pixels. So when we calculate the computation, as small h and w is much smaller than large h and w, the computational scale of UFast can be reduced considerably. For CU lane dataset, UFast computation is 100 times less than original segmentation method. Therefore, UFast achieved low computational cost. Second main method of UFast is lane structural loss for no visual clue problem. No visual clue problem means no information at the target location, so we cannot infer the lane because of no prior lane information. To solve this problem, UFast proposed two more loss functions. The first loss function is for continuous lane. As you can see this equation, by constraining the distribution of classification vector, lane points in adjacent row anchors are close to each other and lane becomes continuous. The second loss function is for lane shape. By using second-order difference equations, the shape of lane is constrained. As a result, by adopting lane structural loss in training, we can find the target location sequentially with lane prior lane information. So, no visual clue problem is solved again. Here are the results of FO measure metrics and result on CU lane. It is observed in table that UFast method achieved the best performance in terms of both accuracy and speed. The fastest model of our formulation achieves 322.5 FPS, and it also shows high accuracy. This result proves the effectiveness of proposed formulation, which is row-based selecting using global features, and structural loss of challenging scenarios because our method could utilize global and structural information to address the no visual clue and speed problem. Thank you for listening.